This video is on differences between strong and weak acids and bases. So this actually is going to tie back into stuff we talked about before regarding electrolytes in solutions, and then connect it with some of the acid-base calculations we were doing in the previous video. So we have to remember or be reminded that all strong acids are strong electrolytes. And remember, electrolyte is anything that conducts electricity, right, in an aqueous solution. And strong electrolytes dissociate 100%, meaning all of their reactants will turn into the products, which are ions. So they will be completely all ions, none of the neutral compound. So dissociate 100% in aqueous solution. All right, so we can talk about acids as being monoprotic, diprotic, triprotic, all that stuff. So what this means is mono means one, protic means proton. So these are acids that have one proton, or another way to say this, they would have one hydrogen, right? Because H plus is a proton. All right, so if we have this right here, this HNO3, this is a monoprotic acid. So it will, and it's a strong acid, so it will 100% dissociate into H plus and NO3 minus. So the H plus then is the molarity of the acid. So what we can think about this is if we have a 0.1 mole per decimeter cubed solution of HNO3, it's going to be the same concentration for our H plus. And I don't want you to necessarily think about this as like, oh, because it's monoprotic, the H plus and the acid concentration are the same. I want you to think about this as this is a ratio of 1 to 1. So it's as simple as the ratio is 1 to 1. They are the same. And I'm actually going to change this. Instead of molarity, let's write the word IB prefers to use, which is concentration. Oops. All right, so a diprotic acid then is one that has 2 protons or 2 H pluses. So any acid that has 2 H's in it. For example, this could be sulfuric acid, H2SO4, 2 H's, so this would be diprotic. First, it dissociates actually like one at a time. So first it's going to happen where one H will leave. Oops, these would have to be aqueous. And then, oops, you'd be left with HSO4 minus. And then that HSO4 minus would lose the other H. Now, what we have here is we have a strong acid here in the H2SO4. But when you get the HSO4 minus, this is a weak acid. So it's not going to dissociate completely. And you'll get H plus and SO4 minus 2, the sulfate ion. Okay. What's really important though is that together, right, if I look at this kind of just overall, what we'll have is H2SO4, right, our diprotic acid, will dissociate into 2 H plus ions and 1 sulfate ion. So when we talk about concentrations, like if I know that this concentration is 0.1, and then I look at, well, what's my H plus concentration? Well, my ratio is 1 to 2, 1 H2SO4 for every 2 H pluses. So this would be twice that. And any pH type calculations I do, I would have to use this 0.2. So there's another level in here. We can't just use this 0.1, whatever our acid concentration is, if it's not monoprotic, like this one up here. Okay, so if I have HNO3, it has a pH of 2.66, find the concentration of the acid. All right, so pH is this. I'm trying to find my H plus concentration, right? And my H plus concentration is going to equal my HNO3 concentration, okay, which will be 10 to the negative pH. So 10 to the negative 2.66. So when I type this in, let's see, I have 2 decimal places, so I'm going to have 2 significant digits in my concentration. So this would be 2.2 times 10 to the negative third moles per decimeter cubed for my concentration of my acid. All right, so let's talk about weak acids. All weak acids are weak electrolytes, right? Which, if you remember, that means they dissociate less than 100%. All right, so if we have something like, we'll just use HA as our kind of generic weak acid, right? And we'll dissociate partially into H plus, whatever A minus is. Okay, so then our equilibrium constant will be our H plus concentration times our A minus concentration all over our HA, our acid concentration. So the larger the Ka is, just like we talked about in our equilibrium unit, larger Ka will favor products because that's what's on top, right? Products over reactants. So a larger product concentration will give you a larger Ka. A smaller Ka favors reactants, or in this case, whatever your acid is. All right, when it comes to diprotic weak acids, it's really just the same as the strong ones, is what you need to know, that it's still something with like 2 H's. Like carbonic acid we have here is going to dissociate the same way, but they're both going to be weak and they're both going to have this. All right, then we get to strong bases, and all strong bases are strong electrolytes. Just like strong acids. So it works the same way. So if we have a strong base like KOH here, and we have a pH, so we're trying to find the concentration of KOH, the POH, and the H+. So a couple ways you can go about doing this. I think the simplest is to find this first, because we've got the pH. So the H+ concentration will be 10 to the negative pH, so 10 to the negative 11.89, which will give me 1.3 times 10 to the negative 12. Oops. And that's moles per decimeter cubed. So then let's see what else. POH might be the next one I would do, because POH is going to be 14 minus your pH. Remember, because they're going to add up to 14. So 14 minus 11.89 will give me 2.11. So now I can find my KOH, because this is a strong base, and it's we're not going to use monoprotic and diprotic, but it has one OH group. So your KOH concentration will equal your OH minus concentration, because that would be a 1-to-1 ratio, which would be 10 to your negative POH, so 10 to the negative 2.11, which gives me 7.8 times 10 to the negative third moles per decimeter cubed. All right, and then the very last piece is that weak bases are all going to be weak electrolytes, just like weak acids. Okay, so one last piece to this. How do you, if you're looking at an acid or a base, how do you determine if it's acid or a base? And then how do you determine, like, reaction-wise, if it's strong or weak? So if you're going to compare things, first, they need to be the same concentrations. So they got to be the same concentrations if you're going to then determine if it's strong versus weak. So a couple things you can do. Oops, sorry about the typo here. Is first, you could measure conductivity. So how much electricity they conduct. Strong acids will conduct more, right? Because they dissociate 100%. You have more ions, conducts more electricity. We looked at this with the light bulbs, if you remember back in our electrolyte unit. You can also measure their pH, and you could use like a pH probe or a universal indicator solution that will change color and give you different pHs, or even pH paper. Strong acids should have a lower value. Okay. And then you could even measure reactions with metals or carbonates. All right, like we talked about in a previous video, kind of what kind of products you'll see. Strong acids versus weak acids. Strong acids will react more vigorously. So what that means is you're going to get more rapid bubbling. That's effervescence. And you're going to get a faster rate of reaction, but that will be harder to observe. All right, so that's just covering strong versus weak acids. Try to relate this back to stuff we already know about with our calculations we just did, and then with the strong and weak electrolytes.